Yeah, thanks for coming. My name is Avik Chaudhuri, and I'm going to talk about what's new in TorchExport. So at PyTorch conference last year, around the same time, we announced TorchExport. It is a mechanism for doing sound whole graph capture of PyTorch models. So you can think of it as a front-end compiler, an ahead-of-time compiler that generates IR without doing any of the back-end optimizations or code generation. Now, why would we build TorchExport, right? What's the benefit of splitting a compiler this way? As it turns out, there are a lot of benefits. So being backend agnostic means that this IR is amenable to any kind of lowering workflow that you might want. So for example, you may want to replace your standard kernels with some custom kernels that are specialized to your own hardware. It is also a stable representation of your code as data. Which means that we have cut all the dependencies that potentially your model's behavior could depend on without changing your model's code in some sense. So we're trying to capture a single representation of your whole model as IR. Also, cutting off Python dependencies is very critical for a lot of environments that are, let's say, memory sensitive or latency sensitive, such as edge or server. So how does TorchExport, how is it different from TorchCompile? So TorchCompile, as you know, you can stick it on top of your model, and it has no program model as such. It will ensure that your code always runs. But the trade-off is that internally, it might only compile certain regions of your code, and it will fall back on an eager Python runtime whenever it cannot compile your code. So these breaks in your code are so-called graph breaks, and it's common to have graph breaks in TorchCompile. It can also make arbitrarily specific assumptions on your code when it's compiling certain regions of your code, and then recompile your code whenever those assumptions change. In TorchExport, we have no such freedom. There cannot be any graph breaks because we cannot fall back to an eager Python runtime. There is no scope for recompiling either, because we have this one shot to capture a representation of your whole model. Right, so TorchExport does come with a program model. So you can get compile time errors, and if you get them, then you have to rewrite your code to fix them. So it's on us, the PyTorch team, to make this process as easy as possible for you. So we strive to give you actionable error messages and even suggest fixes for you sometimes that you can copy paste to rewrite your code. And we also obsess about metrics that measure and try to reduce the number of rewrites you would need to get a successful export. And of course, we are always making TorchExport smarter, so sometimes if we can automate something, and we would not give an error in that case. All right, so over the past year or so, we have been deploying TorchExport in a variety of scenarios inside Meta, and we have gained some valuable insights along the way, and we have made some careful enhancements to the product based on those insights. So this talk is going to talk about those changes. All right, so the first major change has to do with graph breaks. So we used to trace with Dynamo. Now we also trace with a native Python interpreter. And this tracing essentially is a process that takes your model and generates a graph from it. So why did we cool down on Dynamo? As it turned out, a lot of graph breaks that users were seeing were because of unsupported Python features in Dynamo. And I should stress that this is by design, because Dynamo works with TorchCompile, and remember I told you that you can drop down to an eager Python runtime whenever you cannot compile some code. So it's a good fit for TorchCompile. It's just not such a good fit for TorchExport. So now we have this new mode of tracing where we use a native Python interpreter, and by definition it supports all Python features. And so this entire class of graph breaks go away. We think it's a better fit for TorchExport, and it's going to be the default soon. But for now, you can use it by passing in strict equals to false to your export. The next reason you might have a graph break is when you have dynamic control flow in your model. Now, this is not as common as you might think, but when it hits, you have to deal with it. So to address that, we have a growing library of control flow operators You can think of them as normal PyTorch operators, except that they are higher order. They take code as inputs. And with that, we have support for conditionals and while loops. Functional programming fans will find map in there. There's also scan, which is a more powerful version of reduce. These are all inspired by JAX, by the way. So with these control flow operators, you can basically trace multiple paths through your program. So I should say that not all of these operators support every combination of features that PyTorch provides. For example, some of them are missing autograd support, which you need for training. Some of them are missing support from inductor, which is the optimizing backend for Torch compile. But rest assured that we are working hard on these, and by the end of the year, we plan to have full support for this control flow library. Okay, so that's enough about graph breaks. The other reason for having this kind of difference between Torch compile and export is recompiling. So go back to why would Torch compile need to recompile your regions of code? And the most typical reason is that your shapes change over time. But you can get ahead of that by using dynamic shapes to export your program. And with these dynamic shapes, we will not specialize on your shapes of your example inputs that you pass during export, just so that we have this flexibility of accommodating different shapes for future inputs. But the problem still is that your model may not work for all combinations of input shapes. So really the bottleneck is what kinds of conditions do you want or do you expect your shapes to satisfy in order for your code to be correct? Right? So, for example, you may want to impose ranges on your dynamic shapes, or you want to maybe you want to specify that some of these shapes are equal. This was already possible last year. This year, we added support for some more interesting relationships that you can also specify. And these are all checked at compile time. And if you make a mistake, we will suggest the right fix for you, which you just copy paste. But sometimes we encounter models where the conditions get arbitrarily complicated. And we do not necessarily want to bother you with these conditions. So we have this mechanism where if some condition is too complicated, we will just turn them into runtime assertions and not bother you. But if we can do that, then why stop there? Right? So there is some scope for automation here. So we are experimenting with this new feature called automatic dynamic shapes, where we will automatically infer the conditions that your shapes must satisfy for your code to be correct and insert them as runtime assertions. Now, this comes with a caveat that downstream you might have differences in how we can optimize your code, because shape specialization is actually very useful when you can allow it. So in the future, we might provide some tooling that will sample sets of example inputs, figure out which ones should be dynamic, automatically infer the conditions for you, insert them as runtime assertions while leaving a bunch of other shapes static. All right, so that's on input shapes. Now, a new class of errors are becoming common. And these arise when shapes of your intermediate values might depend on data. And in that case, the tracing mechanism cannot make progress. And you cannot specify these as conditions on your input shapes. So what do you do there? So there is an operator called torch.check that will allow you to inline these assumptions inside your code. And when you get this kind of error, we will try to suggest fixes that, again, you can copy paste that will get you, work around these errors. Now, I should say, this is a pretty complicated topic, and we have been thinking about it for several months now. So this is not yet a perfect solution. But if you want to learn more about data-dependent shapes and such, Easy Yang is going to give a talk in this very room tomorrow at 2:15, I think. You should attend that talk. All right, so that's enough about exportability. Let me move to the IR itself. So while we were deploying export in a variety of scenarios, we encountered almost opposing forces on the level of IR you might want. So on the one hand, you might want a small number of low-level operators. And this is great when you're trying to build a minimal runtime that will run all PyTorch models. And this is the state that we were in last year. However, we also found cases where you might want to just capture a graph at the highest possible level because you want to detect and optimize for high-level patterns, and you do not want to reverse engineer this information from low-level operators. So the solution we are moving towards is more of the latter, where we try to capture the graph at the highest possible level in the most general format. But to keep the spirit of the former, we give you very configurable APIs that will allow you to customize how you want to lower this program to a smaller set of operators. And conveniently, this lines up very well with training versus inference scenarios, where for training, you might want to have operators that might even have aliasing or mutating ops in there. But for inference, you want to lower to a smaller offset that are all functionalized. So to summarize, we have two core APIs, one for export and one that we call run decompositions that will decompose your offset to a smaller offset. And then we have two convenience APIs, export for training, which is just export, and export for inference, which is export followed by run decompositions. And in run decompositions, by default, you will have a decomposition table that will take all of your A10 operators and translate them to a small core functionalized A10 subset. But you can tweak this, right? So if you want to preserve some operator, you just find that table, delete a certain entry, and that will cause you to preserve that op. If you want to customize how you want to decompose a certain op, that's also possible using this API. All right, so of course, export integrates into a bunch of runtimes that we built, including AOT inductor and an execute torch. So Martin just gave a keynote on torch chat and how we deploy LLMs, for example, and he showcased both of these. So AOT inductor is for server and more recently for desktops. Execute torch is for edge. But being a standalone IR means that we can also integrate with runtimes that other people built, right? So for example, we have collaborations with TensorRT, Onyx, XLA, TF-Lite, and so these integrations exist, and we hope to keep collaborating and making them better. On the other hand, having a standalone IR also means that you can potentially arrive at it through different means. So TorchScript is still widely used, in particular the front end, where you use JIT-trace or JIT-script to get TorchScript IR. So we are building a converter from that IR to export IR so that you can then plug it into the rest of our stack. So overall, our philosophy is to meet you where you are, right? So we understand that deployment is super hard, and it's also very risky to take your existing stack and fully replace it with a new stack. So we want to build as many entry points as we can so that you can incrementally try our technology and see if it works for you, right? So this is where we are going. We hope that you will help us build more of these entry points, and then we should have a growing and thriving ecosystem around torch export. And with that, I'll end and take maybe a couple of questions.